Okay, so let's go ahead and do a few practice problems. So the first one's kinetic energy. So let's read through the problem and look at our givens. So a 7 kilogram bowling ball moves at 3 meters per second. So I'm just going to stop and identify. So I've got a mass equals 7 kilograms, and I have a speed of 3 meters per second. I'm just going to title this bowling ball. And how fast must a 2.5 gram ping pong ball move in order to have the same kinetic energy as a bowling ball? And the second part of the question, is this speed reasonable for a ping pong ball in play? All right, so I also have a ping pong ball that has a mass of 2.45 grams, which I know I need to convert to kilograms. So I'm going to move the decimal place 3 times to the left. 1, 2, 3. So it's going to be 0.00245 kilograms. And I need to know what the speed is. All right, so to do this problem, I have to figure out what is the kinetic energy of the bowling ball. We know that the equation is Ke equals 1/2 mv squared. So let's go ahead and plug in and solve. So 1/2 of 7 times 3 squared. Alright, so we've got 0.5 times 7 times 3 squared equals kinetic energy of 31.5 joules. So the kinetic energy of this bowling ball is 31.5 joules. Alright, now the question asks, how fast must this ping pong ball move in order to have the same kinetic energy? So to solve this one, we know that we want the kinetic energy to equal 31.5, and we would need to know, okay, how fast does this ping pong ball need to move? So we got 31.5 equals 1/2 of 0.00245 times v squared. So I'm going to go ahead and multiply 1/2 times 0.00245, and then I'm going to divide 31.5 divided by that answer. And on the left side so far I get 25,714.28 equals v squared. And then without rounding, I'm going to find the square root of that answer, and I get a speed of 160 meters per second. I'll let you guys convert that into miles per hour or look it up online to figure out, is that a reasonable speed for a ping pong ball in play? 160 meters per second. All right, let's go ahead and move on. Work kinetic energy theorem practice problem. So a student wearing frictionless inline skates on a horizontal surface is pushed by a friend with a constant force of 45 newtons. All right, I'm just going to stop here. I know that F is 45 newtons. How far? All right, so I know what I'm looking for. I'm looking for displacement. Must the student be pushed starting from rest? Okay, that's important. So if I'm starting from rest, what does that mean for my initial kinetic energy? Well, if you're not moving, you're not going to have kinetic energy, so 0 joules. So that her final kinetic energy is 352 joules. So I know that KEF needs to equal 350 joules. So I'm going to go back up here real quick and just look at my work kinetic energy theorem. There's several ways that we can look at this. And I see that FD, okay, so on the left side I know I have force, I'm looking for displacement. So on the left side I know I need FD, so FD. And then on the right side I can have the changing kinetic energy, I can have final minus initial, and I can have 1/2 mv squared minus 1/2 mu squared. We're actually given the full kinetic energy, so I can use the final kinetic energy minus the initial kinetic energy. The initial kinetic energy is equal to 0, so really all I'm left with is the final kinetic energy, and I can plug in 45 times displacement, because that's what I'm looking for, equals the final kinetic energy, which we were told is equal to 352. So this problem ends up being really easy. Divide by 45, and we get a displacement of 7.822, so I'm just going to leave it at 7.8 meters. Now let's go ahead and do a gravitational potential energy problem. So a 40 kilogram child, so I know that M is equal to 40 kilograms, is in a swing that is attached to ropes 2 meters long. Okay, so I know height is 2 meters. Find the GPE, or gravitational potential energy, associated with the child relative to the child's lowest position under the following conditions. All right, so when the ropes are horizontal. All right, so meaning that if we have our swing and the rope and we're horizontal, right, so that means if the ropes are 2 meters long, and we can assume that, let's just assume, we'll call this like where the resting position would be, let's just call that 0. So this height is 2 meters. All right, so we're going to call this height 2 meters. So problem A, when the rope is horizontal, we need to figure out what the GPE is. So potential energy is equal to mgh. Well, we were told the mass is 40. We know that gravity is 9.8, and we're plugging in a positive 9.8 here because it's a scalar. It doesn't really matter, positive, negative, times the height of 2 meters. So we've got 40 times 9.8 times 2, and our gravitational potential energy is 784 joules. So that was A. That was problem A. And then B, at the bottom of the circular arc. Well, okay, if this was horizontal, then here's our swing, then it's just resting right here. So we called that, we don't know the distance between the bottom of the seat and the ground, but we can call that 0 because the max height was here when the swing was horizontal, and then here it's at the bottom. Well, let's think about this. If we're all the way at the top, we're pulled back, right, gravity has a chance to work on this. It's at the top of its swing, but here it's at the bottom of its swing. Right? So we haven't really talked about the conservation of energy yet, but if you have all of your potential energy up here, energy is going to be transformed into kinetic energy, and you're going to be at your max kinetic energy at the bottom. So if you're at your max potential energy, that means you don't have any potential energy left. So at the bottom of the circular arc, we can call this 0 because, so at the bottom, our potential energy is equal to 0 because all of our potential energy has been converted into kinetic energy at the bottom of the swing.